Welcome to the Deep Dive. Today we're starting with a really great quote from Nassim Nicholas Taleb. He says, "Never cross a river that is on average 4 feet deep."
That's a good one.
It really makes you think, doesn't it? I mean, an average of 4 feet. Yeah, maybe some spots are 2 feet, easy, but others could be, 10 feet deep? You just don't know from the average alone.
Exactly. That average hides, potentially dangerous details. And that idea, averages masking the reality for individuals. That's really the heart of our deep dive today.
So what are we digging into specifically?
We're exploring something called heterogeneous treatment effects. It's a bit of a mouthful, but the core idea is simple. Instead of just the overall average impact of something, say a new policy,
Right.
we want to understand how that impact changes, sometimes wildly for different people or different subgroups.
Okay, so moving beyond the single number, and that leads us to the conditional average treatment effect.
Kitty, exactly. If the average effect, the AEE, is like that wide shot of the river, K is like zooming right in. It asks, how deep is the river for you right where you're standing?
Based on things we know about you, your characteristics.
Precisely. So our mission today is, first, to explore why understanding these different effects is so critical. It's not just academic, right?
Definitely not.
Then look at the statistical hurdles, because it's not easy. And finally, how new tools like machine learning and AI are basically revolutionizing how we estimate these Kates.
Which lets us create more personalized and hopefully much more effective policies.
That's the goal. And just for context, our discussion today is grounded in a really solid academic paper, Applied Causal Inference, powered by ML and AI. It's by Viktor Chanozikov and colleagues, just published online, March 5th, 2025.
Great. So, K80, we know what it is. But let's really hammer home the why.
Yep.
Why is just looking at the average, the ADE, the unconditional average treatment effect, potentially so problematic?
Well, think about it. You roll out a new program, maybe educational, maybe financial. The overall average effect, the ATE, might look positive. Small, maybe, but positive.
Which sounds okay on the surface.
Right. But dig deeper, and you might find that certain groups, maybe based on income or location or background, are actually being harmed, like their outcomes get worse.
And the average just smooths over that harm, hides it.
Completely hides it. You could be, unintentionally making things much worse for a vulnerable subgroup, even while the average looks acceptable.
And the flip side is true too, isn't it? What if the average effect is 0? Or even negative?
Yeah, that's just as bad, potentially. You might look at that 0 average and say, okay, this policy doesn't work, let's scrap it.
But maybe it works incredibly well for a specific group.
Exactly. There could be responder subgroups hidden in there who would get huge benefits, but they get denied those benefits because the average for everyone else drags it down.
So ignoring this heterogeneity, these differences, it can mean actively harming some people, or just as bad, withholding benefits from others who really need them.
That's the core problem. And that's where Kates really show their power. They let us use data to find these varied effects, to discover, who benefits, who doesn't, maybe who's harmed.
All driven by the data itself.
Right. And the ultimate aim, really, is to enable personalized policies, tailoring interventions based on characteristics we can actually see and measure.
We see this a lot already in certain fields, right? Like online.
Oh, absolutely. Digital experiments, targeted marketing, that's all about Kate. Companies aren't just sending one ad to everyone. They're constantly trying to figure out which ad works best for this type of customer versus that type. That's ATE estimation in action.
Makes sense. But you mentioned statistical challenges. Why is estimating Kates so much harder than just getting that one average number, the ATE?
Well, fundamentally because the kite isn't a single number. It's a function. It describes how the treatment effect changes as individual characteristics change. Think income, age, education.
So you're trying to map out a whole landscape, not just find a single peak elevation.
That's a great analogy. And estimating a function accurately, especially when it might depend on many, many characteristics, is statistically way more demanding. We're not just looking for a good guess. Often we want reliable confidence intervals around that function. We want to know how certain we are.
Which is a much higher bar than just finding the average.
Much higher. And because of this complexity, researchers often have to recalibrate their goals a bit when trying to estimate Kates. The paper actually lays out 4, maybe 5 main ways to approach this.
Okay, so given it's so complex to estimate this whole Kate function, what are these different avenues? You mentioned targeting best linear approximations or BLAs. What's that about?
Right, BLAs. So instead of trying to capture every single little wiggle in the Kate function, which might be incredibly complex, you aim for something simpler. You try to find the best linear function, or maybe a simple curve that approximates the true Kate.
So like drawing a straight line trend through noisy data points.
Kind of, yeah.
Yeah.
Or maybe a simple polynomial curve. The big advantage is that for these simpler approximations, we have really solid statistical methods to construct confidence intervals, even what are called simultaneous confidence bands that cover the whole approximation at once. It makes the inference part much more manageable.
You trade off some complexity for statistical robustness, basically. Makes sense. What's another avenue?
Well, sometimes you don't need the whole function, even an approximation. You might be interested in specific summaries of the Kate. For example, what's the average effect just for people in the bottom 10% of income? Or what's the overall value if we implemented a policy based on the Kate estimates?
So focusing on specific questions about the distribution of effects.
Exactly. Then there's the third approach, trying to get non-parametric confidence intervals for the KT at specific points.
Okay, this sounds like getting back to that pinpoint accuracy for individuals.
It is, and this is where methods like causal forests, which we'll definitely talk more about, come in. They merge ML with uncertainty quantification, but, and this is a big but, well, it's just that these methods, theoretically, they work best when the number of characteristics you're conditioning on, the X variables, isn't too large, and in practice, they can be a bit more, let's say, brittle. Their validity depends on more assumptions holding true.
Okay, so powerful, but maybe need to be handled with care. What's the fourth avenue?
The fourth one sort of shifts the focus again. Instead of prioritizing confidence intervals for the Kate function itself, it prioritizes prediction accuracy, getting the Kate estimate itself as accurate as possible, usually measured by mean squared error.
Like a standard machine learning prediction task.
Pretty much. But because you might lose those direct confidence intervals on the Kate estimate, you then rely on different tools like special out-of-sample tests to check if your Kate model is actually useful. Does it really capture significant differences in effects? Does using it lead to better policy outcomes?
So validating the model's overall performance rather than the precision at every single point.
No.
That sounds related to a fifth perspective you hinted at earlier.
Yeah, exactly. The fifth way to think about it is to focus almost entirely on the policy goal. Often, for making a decision like, should this person get treatment A or treatment B, you don't need to know the exact size of the effect.
You just need to know if it's positive or negative for them.
Precisely. Is the effect positive or negative? Learning the sign of the Kate is often enough to partition the population effectively. So it shifts the problem. It becomes less like a regression problem predicting a value and more like a classification problem. Are you a responder or not?
Putting people in the right bucket. That makes a lot of practical sense.
Yeah.
Okay, let's dive into some of these methods more deeply, starting with those best linear approximations, the BLAs. How do they actually work in practice?
So the goal, remember, is to take a potentially super complex Kate function, maybe depending on dozens of variables, let's call them Z's, and summarize its relationship with a few key variables of interest, X.
Like focusing on how the effect changes just with income, even if other things matter too.
Exactly. The paper uses that 401k eligibility example again. Y is household financial assets. D is being eligible for a 401k. Z is all the household characteristics they measured. But they choose X to be just income. They want that simple summary. How does 401k eligibility impact assets as income changes?
Got it. And the technique they use is called dual machine learning, DML.
Right, DML for Tate. It's a really clever, kind of generic two-stage approach. First stage is about cleaning up the data, essentially. You use machine learning, often with cross-fitting.
What's cross-fitting?
It's a way to avoid overfitting. You split your data into parts, say K-folds. To make predictions for one fold, you train your ML models only on the other folds. It helps get more honest predictions.
Okay.
So you use ML and cross-fitting to estimate these sort of nuisance components, like the probability of being treated or propensity score, or the expected outcome without treatment. Then you combine these pieces to create a new special variable for each person, often called Y tilde.
And this Y tilde is like the core signal of the treatment effect for that person. Purified.
That's a good way to put it. It's designed to be an unbiased signal for the treatment effect, removing the influence of confounding factors estimated by the ML models. That's step one.
Okay, step 2.
Step 2 is surprisingly simple, actually. You just run a regression. You regress that clean signal, y tilde, onto the features you care about, your X variables like income in the 401k example.
And that regression gives you the best linear approximation.
Yes. Or more generally, an approximation based on whatever basis functions you use for X in that second regression. And crucially, because of how y tilde was constructed in step 1, using something called Neyman orthogonality.
Okay, technical term.
Yeah. Don't worry too much about the name. The point is, this structure makes the second step adaptive. It means the statistical inferences you draw from that second regression, like your confidence intervals for the BLA, are almost as good as if you magically knew the true propensity scores and outcome regressions perfectly from the start. The errors from the first ML stage don't mess up the second stage inference too much.
Wow, okay. That's pretty smart, using ML to clean things up so that a simpler second step works reliably.
Exactly. And within that second step, when you're learning the Kate approximation, you typically use least squares. You approximate the Kate using a combination of basis functions.
Like polynomials.
Could be polynomials of income, or splines, which are like flexible curves, or a really interpretable type group indicators.
Like dividing income into groups. Quintiles, maybe.
Precisely. If your basis functions are just indicators for, say, income quintiles, bottom 20%, next 20%, etc., then the coefficients you estimate in that second stage regression are exactly the group average treatment effects, or gates, for each income group.
And the paper shows results for that with the 401k data, right?
Yes. They show the estimated gate for each income quintile. You see the point estimate, like the average effect within that group. And then the confidence bands, they show narrow red lines.
Those are the point-wise bands.
Right. Good if you only cared about one specific group beforehand. But they also show wider box bounds. Those are the uniform confidence bands.
Covering all 5 groups simultaneously. So you can be confident that the true gate for all those groups lies within their respective boxes all at the same time.
Exactly. It's a stronger guarantee if you're looking at the pattern across all groups. They also show an example using a polynomial of log income instead of groups.
So a smooth curve instead of steps.
Yeah. You see the estimated curve, the point estimate, then dashed blue lines for the pointwise confidence band at any single income level, and wider solid blue lines for the uniform band that covers the entire curve simultaneously.
That distinction between pointwise and uniform seems really important for interpretation.
It absolutely is. It tells you how much confidence you should have in a single point versus the overall pattern.
Okay, that gives us a good handle on BLAs and DML. Now, moving to those more complex non-parametric methods like causal forests, you said getting confidence intervals at specific points is harder here.
It is, statistically speaking. Standard random forests are great predictors. They balance bias and variance nicely, but they don't automatically give you valid confidence intervals for their predictions.
So how do causal forests manage it? What's the magic?
Well, it's not quite magic, but clever adaptations based on what are sometimes called honest random forests. There are a few key ingredients. One is honesty itself. It means you use one part of your data to decide the structure of the trees where to split, and a completely separate part to actually estimate the effects within the leaves of the trees.
So the tree structure isn't biased by the outcome values it's trying to predict later.
Exactly. Another is balancedness, making sure splits don't create tiny, unstable groups. They also use random feature selection and grow the trees quite deep. And importantly, they often use subsampling without replacement, rather than bootstrapping, which turns out to be better for the theory behind the confidence intervals.
Okay, so several tweaks to the standard random forest algorithm. And you mentioned doubly robust forests.
Right. Those are basically honest forests, but they're trained on that clever y tilde signal we talked about from DML. Using y tilde makes the resulting confidence intervals robust, even if the ML models used to create y tilde weren't perfectly accurate.
Which is useful in the real world, where models are never perfect.
Definitely. And then there's the broader framework of generalized random forests, or GRF, which causal forests are a specific type of.
How do GRF work?
GRF frames the problem slightly differently. It thinks about finding splits in the data that maximize the differences in treatment effects between the resulting groups. It's actively looking for heterogeneity.
So the splits are designed to reveal where the effect changes most.
Exactly. Then, to estimate the Kate at a specific point x, it looks at all the data points that frequently ended up in the same tree leaves as x across the whole forest. It calculates a weighted average effect using these similar points, where the weights reflect how similar they are according to the forest structure. Causal forests are just a very popular, well-implemented version of this, specifically for treatment effects.
Okay, let's see it in action. Back to the 401k example. How did forests perform there?
They applied both doubly robust forests and causal forests using all the available household characteristics, letting the algorithms figure out what mattered. And interestingly, both methods found a very similar pattern for Kate based on income.
Which was?
That the positive effect of 401k eligibility on financial assets was larger for households with higher incomes.
That makes intuitive sense.
It does. And the forest methods did something interesting at the income extremes. Instead of just extrapolating linearly, they showed the effect sort of leveling off at both low and high incomes, forming more of an S shape or sigmoid curve, which seems more realistic.
And they could see where uncertainty was highest.
Yep, the confidence intervals widened noticeably at the very high end of the income distribution, reflecting the fact that there's just less data up there. And crucially, when they looked at which features were most important for driving these differences and effects.
Let me guess. Income.
Income was number one. The forest confirmed it was the key dimension of heterogeneity in this case.
Very cool. Now, what about that welfare experiment? That sounds fascinating.
It really is. So this was a proper randomized trial within the General Social Survey. People were asked about satisfaction with government spending, but randomly got one of two phrasings: welfare programs or assistance to the poor.
Same underlying topic, different frame.
Exactly. They had data for almost 13,000 people, their response, which version of the question they got, and 42 other features: demographics, education, income, occupation, and importantly, political views.
And the overall average effect, the AEE.
The average effect of using the welfare phrasing was negative 0.37, Reagan 0.3681, meaning on average, that word significantly reduced stated satisfaction with spending.
Okay, so welfare is a loaded term, on average. Did the forests find differences across people?
They did. They threw all 42 features into the causal forest and doubly robust forest models. And overwhelmingly, the single most important feature driving heterogeneity in the treatment effect was
Political views.
political views. Both methods flagged it as the key factor. The effect of the word welfare depended significantly on someone's self-reported political stance. The paper shows plots illustrating the estimated Kate for each level of political view, along with confidence intervals.
That's a powerful finding. It shows why the average effect is what it is and for whom the framing matters most.
Precisely. But again, the practical caveats apply. While these forest methods are incredibly powerful for discovery,
They can be brittle.
yeah, the uncertainty estimates, the confidence intervals, can be more sensitive to assumptions and tuning choices compared to, say, the BLA methods. They definitely give a meaningful signal of uncertainty, but maybe need a bit more careful handling in practice.
And getting those nice uniform confidence bands, like for the BLA curves, is much harder for these complex forest-based Kate functions.
Extremely challenging, yes. Often, researchers have to settle for bands that cover a simply approximation of the Kate function, not the full, complex beast itself. It's still an active research area.
What a journey. We've gone from seeing the real dangers of relying on simple averages to understanding how these conditional average treatment effects, these Kates, give us such a richer, more personalized picture.
Absolutely. We saw how best linear approximations can provide robust, interpretable summaries like those Gates by income group.
And then how these advanced causal forest methods can really dig into high-dimensional data to automatically discover what drives differences in effects like income in the 401k case or political views in the welfare framing experiment.
And the implications are huge, aren't they? Thinking about how to design policies that are not just effective on average, but are fair and beneficial, or at least not harmful, across different groups. It's about moving towards more targeted, ethical, and ultimately more effective interventions.
It really brings us back to that Taleb quote, "Never cross a river that is on average 4 feet deep." Ignoring heterogeneity is like wading into that river without knowing where the deep spots are. CADI analysis helps us map those hidden currents.
It helps us see the 2-foot shallows where we can cross safely and the 10-foot depths to avoid. It lets us navigate smarter.
So the thought to leave you all with is this. Thinking about policies or interventions in areas you care about, maybe healthcare, education, climate change, whatever it is, how might understanding these deep currents, these heterogeneous individual responses, reshape how we approach those challenges?
Yeah, how could that personalized understanding lead to better outcomes? It's a powerful question. And for anyone who wants to get their hands dirty with this stuff,
Yes.
the paper does mention there are R and Python notebooks available online that actually replicate the 401k and welfare examples using these methods.
Oh, fantastic. So you can try it out yourself. We'll make sure that info is accessible. Definitely something to check out if this deep dive sparked your interest.